Hey there, Calc 2 folks. I wanted to go through the next bit of material here in our study of sequences and series. And that is looking at our first four tests, right? Where we can use these tests to help determine whether an infinite series is convergent or divergent, right? Before we spend the time trying to evaluate that infinite series. If we know ahead of time that infinite series is divergent, we are not going to necessarily spend the time trying to evaluate it, knowing that it would just add up to the value of infinity. Whereas if we knew ahead of time that a series was convergent, we would certainly know that it would be worth the effort to spend the time trying to evaluate the series, or at the very least beginning to approximate the series. And we are going to see some approximation techniques also develop here in some follow-up material. Now, again, what I do want to show you here are our first four tests. These do appear in sections 10.4 and 10.5 material. The first one being here, what you see up on the screen, which is in section 10.4, it's known as the Divergence Test. It is a test of an infinite series to determine whether the series diverges, folks. To begin with, this test does not help us determine convergence. It only helps us to determine divergence. Now, it is presented as a theorem. If you read that theorem, it says, if a summation from k to infinity, now you will notice in this summation here, I did leave off the lower subscript because this can actually be true starting at any lower, I should really say, index value for k. This could be true for k equal to 0, k equal to 1, k equal to 2, and so forth. So how we state that just in general is from k. From k to infinity, we're looking at the summation for a sub k. And if the summation from k to infinity for a sub k converges, right, then what is going to be true is the limit as k heads to infinity for a sub k is going to equal 0. Now, folks, this statement here is an if-then statement, which means the if condition has to be true before we can draw a conclusion about the then condition being true. In an if-then statement, however, what we want to keep in mind is just because the then statement might happen to be true, there are no guarantees that that makes the if statement also true. In an if-then relationship, only if the if statement is true will then the then statement also be true. It doesn't go backwards the other way, where if the then statement is true, the corresponding if statement is also true. All right? Just because a limit of the terms of a sequence as k heads to infinity equals 0 isn't going to guarantee the case for convergence. Now, you're going, how is any of this helpful? Well, what we're going to rely on, folks, is what we call the contrapositive of that statement. All right? The contrapositive is what we have as the equivalent statement here. All right? It states, if the limit as k heads to infinity for the terms of our sequence do not equal 0, then what must be true is that our sequence is not convergent. And what is it to be not convergent? Well, that is going to be the case for divergence. So equivalently here, this is what we call our test for divergence, this actual equivalent statement. What we're going to do to determine if a series diverges is we're going to look at the limit as k heads to infinity for the terms of that sequence. And if they happen not to equal 0, we can then conclude that that series must diverge. All right. Now, I will tell you, if you calculate this limit and it equals 0, the test is actually inconclusive, is how we approach that result. Now, if we look at the case, let me bring up an example here. We might consider the case for the series, all right, given by just the summation from k equals 1 to infinity for k. Now in this series, we would be taking 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so forth. And obviously, this is a divergent series, right? If we were to continue adding up the integer values starting at 1 and continuing up to infinity, that would obviously add up to infinity, right? It's kind of obvious that this is a divergent series. And this can be shown using the divergence test. If we took note, the limit as k heads to infinity is not the value of 0. So by the divergence test, we must be able to conclude this series diverges. All right? Again, the divergence test can only be used to show that a series diverges. All right? It cannot be used to draw a conclusion about convergence. All right? If we look at another example here, where is this example? Bring this up. We might consider the series given by the summation from k equals 0 to infinity for 2 times k divided by 3k plus 1. Now, if we spend a moment evaluating the limit as k heads to infinity for the terms of this series, what we will notice is that that does by a couple of different methods. We could rely on L'Hopital's rule here, or we could rely on some fundamental rules for rational forms involving limits. The result here is the value of 2/3 for this limit, which also does not equal the value of 0. So by the divergence test, what we can conclude is that this series must diverge. Again, the divergence test can only be used to draw conclusions about divergence, right? It cannot be used to determine a series as convergent, right? Let's look at another example here. Note, I do make this note, if the limit as k heads to infinity for a sub k equals 0, the result of the divergence test yields what we call inconclusive result for the infinite series. There does not exist a divergent series, right? Or careful there, let me go back. There does exist divergent series where when you evaluate this limit, right, the limit as k heads to infinity for a sub k, it equals the value of 0. One of these cases for this divergence series where this limit equals 0 and the divergence test gives an inconclusive result is the case for what we call the harmonic series, right? The series from k equals 1 to infinity for the argument 1 over k is known as the harmonic series. This is actually the series equivalent to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so forth. Right? This is what's known as the harmonic series. And if you just spend a quick moment with it, evaluating the limit of the terms as k heads to infinity, you would see that they do equal 0. But I will tell you that the result of the divergence test here is actually inconclusive, right? It can actually be shown using our next test, which is going to be the integral test, that this harmonic series is the case for a divergent series. So folks, when applying the divergence test to determine if a series diverges, right, you are just going to evaluate the limit of the terms and consider the case for when they do not equal 0. In that particular case, you do have the case for divergence. If the limit does equal 0, you are going to have the case for an inconclusive result. And you're going to have to rely on some other technique to determine convergence or divergence. In the case of the harmonic series seen down here, we're going to have to rely on the technique known as the integral test, which is our next test in this. Hey there, Calc 2 folks. I'm back here with the second portion of our study here of the tests for convergence and or divergence of infinite series. As I had noted in our last video, that the next test we were going to take a look at that occurs in section 10.4 is what's known as the integral test. And as the name might imply, it does involve a little integration, right? And we see that presented here in the following theorem, right? The way this theorem begins, right? It does start off with the assumption that you're dealing with an infinite series. It starts at a lower index of k equal to c and continues up to infinity for a sub k, right? Where in this case c is any constant. This lower index is just any constant, right? If the arguments of that series can be expressed as a explicit function of the index k, where if we think about that function in the context of our rectangular system, where y would be equal to f of x, and that function being then thus continuous, positive, and decreasing for values of x greater than or equal to this value of c seen as the lower index, then what must be true is that the sequence, or the infinite series whose terms are a sub k, and the improper integral from c to infinity, where the integrand is given by f at x, where f is the explicit function describing the kth term in our infinite series, right? Then what must be true is that these two corresponding infinite series and improper integral are either going to both converge or both diverge in value. If you recall, back at the end of chapter 8, we looked at improper integrals, and there are two types of results we could have for a case of an improper integral. And in this particular case, we have an improper integral due to the fact that our upper bound in this integration is heading towards infinity, right? And what can happen in an improper integral is that you could converge in value, or it might diverge in value. And the convergence or divergence of this improper integral, whose function, right, is defined by the explicit function of our corresponding infinite series, right? If it converges, then so does this corresponding infinite series, whereas if this diverges, so does the corresponding infinite series, right? In the case of convergence, though, we do want to keep in mind the convergent value of our improper integral is not necessarily going to be equivalent to the convergent value of our infinite series. We may find that this improper integral converges to one value, and that is not necessarily going to be what the value of the corresponding infinite series is in value. If it does happen to be that in value, it is strictly coincidence, right? Now, as we had highlighted in the end of the previous section, this integral test can be used to show that the harmonic series is actually the case for a divergent series, right? As we had noted in the previous test, looking at the case for the divergence test, if I apply the divergence test on this infinite series, it does produce an inconclusive result. And I had noted that the way that we're going to go about showing that the harmonic series either converges or diverges is using the what we call integral test. To actually perform the integral test here, what we're going to do is take the functional description of our arguments in terms of k and consider calculating the improper integral for those arguments, where the bounds on that integration will go from our lower index of 1 up to infinity, and the integrand will take on the form of 1 over k, where k has been replaced with the independent variable x. And we're going to calculate the behavior of this improper integral. And keep in mind, when we saw this back in chapter 8, we were going to approach this as a limit. A limit is b heading to infinity, b being the upper bound on this definite integration, where if we follow the rules of integration here, right, the antiderivative of 1 over x is going to be the value given by the ln of x. If we evaluate that across the bounds from 1 to b, that's going to result in the ln of b minus the ln of 1. And what do we know about the ln of 1 is that it's equivalent to 0. So really, this is just an argument given by the ln of b, where we're interested in the limit as b heads to infinity in the ln of b. And what is that limit's value? Well, it happens to be infinity, indicating that the integral, the improper integral from 1 to infinity for 1 over x dx is divergent. And thus, by the integral test, our corresponding infinite series given by the harmonic series must also be a case for divergence. Right? That is what we know as the integral test. Given an infinite series, we're going to consider the corresponding improper integral, right, where the integrand, right, is the explicit function of the arguments of our infinite series expressed in terms of x, and our definite integral in that improper integral, or that those bounds in our definite improper integral, are going to go from our lower index of 1, or c, up towards infinity. All right. If we look at another example here, let me bring another case into view. All right. We might consider this case here. The case for the summation from k equals 1 to infinity for 1 over 4k plus 3 quantity squared. Right? The corresponding value of the improper integral in this case is going to be the integral from 1 to infinity for 1 over the quantity 4x plus 3 squared, where we're just taking the integrand expressed as this explicit formula in terms of the index k and making it the integrand in our integral in terms of x. We're to again evaluate this improper integral. We are going to apply a limit as b heads to infinity, b being the upper bound in our integration. And to integrate this, we are going to rely on a little u substitution. All right. We can see here, letting u equal 4x plus 3, du dx will equal 4, which will imply 1/4 du will equal dx. So inside of the limit of inside of the integral of 1 over 4x plus 3 squared dx, that can be rewritten as 1/4 times this limit as b heads to infinity for what would be the integral now from 7 to the quantity 4b plus 3. We get those new bounds by taking our old bounds of 1 and b and substituting them into this argument for u. And u replacing the 4x plus 3 can be thought of as u to the negative second power as our new integrand, and all integrated with respect to u. The 1/4 du replacing this quantity of dx. Now if we evaluate the antiderivative of u to the negative second power, that is negative 1 over u, where we're going to evaluate that from 7 to 4b plus 3, which does yield negative 1 over 4b plus 3 plus 1/7, where if we now evaluate the limit of that as b heads to infinity, it does result in 0 plus 1/7, or 1/7 in value. When multiplied by that constant multiple of 1/4, it yields the value 1/28. Thus, by the integral test, since the integral from 1 to infinity for 1 over 4x plus 3 squared dx converges to 1/28, we can also say the corresponding infinite series must also converge. Again, that is the integral test, folks. We can go on to take note. The integral test can actually be used to prove the result in the following theorem for convergence of what we call P series. By definition, a P series is just a series in the form given by the summation from k equals, from k to infinity for 1 over k to the pth power, where p is any real number power. All right. This series that takes on this form, where we're working with an index of k raised to the pth power in our denominator, is what's known as a P series. All right. For example, the harmonic series given by the series from k equals 1 to infinity for 1 over k is a case for a P series where p equals 1. Whereas the series given by the summation from k equals 1 to infinity for 1 over k squared, that's the case for a P series where p is equal to 2. And the series given by the summation from k equals 1 to infinity for 1 over the square root of k, Well, that's a case for a P series where P equals 1/2. All right? Each of these three series all being examples of a P series with some different given value for P. Now, this is a special case of a series where we have the following notation about, or note about the divergence or convergence. And it's presented here in the following theorem. The P series, given by the summation from k to infinity for 1 over k to the pth power, is convergent when that power of P is greater than 1. And correspondingly divergent when P is less than or equal to 1. Right? This value of P will tell us whether we converge or diverge. And if we go back to the harmonic series, in that case, P was equal to 1. And since P equal to 1 is less than or equal to 1, that harmonic series must be a divergent P series, which we've shown it is using the integral test. The integral test. And the same would be true for that series given, that P series given where P is equal to 1/2, right? Because 1/2 is less than or equal to 1, this summation from k equals 1 to infinity for 1 over the square root of k is also a divergent series. Whereas for the value 1 over k squared, right, it is the case for a convergent P series, since P would be equal to 2, and 2 is greater than 1. Right? Now, the integral test is what allows us to prove this result for convergent P series. If we were to look at the proof, here's the proof, that's what I end with here, and we consider the summation from k equals 1 to infinity for 1 over k to the pth power, and take note, when P is not the value of 1, the result for the integral test is going to result in, if we calculate it here, this result down here, 1 over the quantity 1 minus P times the limit as B heads to infinity for 1 over the quantity B to the P minus 1 power minus 1, where the convergence or divergence of this infinite series is going to essentially depend upon how this value behaves inside this limit. All right. If we consider that value inside that limit, right, as for the convergence or divergence of this limit, that will depend upon the behavior of this, the limit as b heads to infinity for this very first term. And note, this limit converges to 0 when p minus 1 is greater than 0, implying p greater than 1, implying p would be greater than 1, producing this result for convergence. And whereas this limit diverges to infinity when it is the case where p minus 1 is less than 0, implying that would be the case for p being less than 1. All right? Depending on how p behaves here will determine whether this limit here converges or diverges, whether it approaches a real number value or whether it converges off to infinity. And it'll converge off to infinity when p is less than 1, and it'll converge on to 0 when p is greater than 1. As for what does it do when p equals 1, we've actually shown that that is the case for divergence. Again, when p equals 1, that is the divergent harmonic series, which was in our first example in this set of notes. All right, folks, this is the integral test, and it looks at the convergence or divergence of a corresponding improper integration, right, where in the integral of that integration we are essentially expressing the explicit formula for the kth term of our infinite series, right, in terms of some function of x. And whether or not this improper integral converges or diverges will determine whether or not our corresponding infinite series converges or diverges. We saw that here with the harmonic series. We saw that in the case of that second example, that case of this series here. And it sets us up for proof of what we call the convergence of P series, where the P series is a unique case of a series where we can determine the convergence or divergence of the series by simply examining the power of P, right? I will tell you, having some information about the P series and its behavior is going to be helpful in our next set of tests, looking at the comparison tests. In the comparison test, we're going to want to be familiar with some simple cases of convergent or divergent series that we're going to compare complex series to in order to determine their convergence or divergence. And depending upon the convergence or divergence of our simple series, will help us determine the convergence or divergence of these more complex cases. Now, this is what's going to develop in our comparison tests, which is going to be the next two tests that we see presented in section 10.5. So I'll give you a quick little break over now, and we'll get back to those comparison tests shortly. See y'all then. Bye. Hey there, Calc 2 folks. I'm back here with another quick little lecture over what are going to be our first four tests for convergence and divergence of infinite series. And that is the case for the comparison test here, folks, which we see presented in section 10.5 of the book. Right? 10.5 actually presents two different cases for the comparison test. It just presents what we call the comparison test. And it also presents what's known as the limit comparison test. That is the video that will follow this, folks. But right now, we're just going to spend the moment looking at what we call the just alone the comparison test, right? In either of the comparison tests that we're going to see, a big portion of the test is going to involve comparing a given infinite series to another infinite series where we happen to already know the behavior of this other infinite series, right, that we're comparing to. In the notation, what we'll often talk about is having these two series A sub k and series B sub k in the comparison tests, where in terms of these two series, the infinite series given by A sub k or denoted by A sub k is going to be our given series. It's the series whose divergence or convergence we're trying to determine. Whereas what we are going to compare it to, the series whose behavior we're already familiar with, is going to be this the series denoted with the sequence B sub k as its terms, right? So what you will see is this very first theorem starts off by just noting let series A sub k and let series B sub k be two infinite series with positive terms. Now, we will see this idea of positive terms also thrown into these tests, folks. What we do mean by that is we're not dealing with a case of alternating series. We're going to see alternating series presented in a future section here of Chapter 2. What we're considering are the cases for non-alternating series. Well, if we consider having these two non-alternating infinite series, the first result in the comparison test, or the first part of the comparison test, might go along, or it does go along and state that if initially series A sub k, or really I should say the terms of sequence A sub k, are less than or equal to B sub k, all right? If the terms of A sub k are less than or equal to B sub k, and it's so that B sub k is convergent, what must also be then true, right, is that our given series A sub k is also convergent, right? If we're working with comparing to a series that we know is convergent, and the terms of the sequence in our given series are always smaller than the terms in that convergent series, what we can conclude about our given series is that it must also be this case for convergence. Right? That's the first part of the comparison test. Whereas the second part gives us a situation involving divergence. If it so happens that the terms of sequence A sub k are greater than or equal to B sub k, and the sequence we're comparing, the series we're comparing to, series B sub k, is a divergent series, then what we're going to be able to conclude is that our given series A sub k is also divergent. Right? If we have a divergent series that we're comparing to, and the terms of that known divergent series are always smaller than or equal to what would be the terms of the given series, right? Given that these terms are always smaller than and divergent in behavior, we're able to conclude that the given series is also divergent, right? These are known as the comparison tests, folks. They can be used to draw conclusions about convergence or divergence of given infinite series. If I bring an example into view here, all right, we might consider the behavior of the infinite series here, given by the summation from k equals 1 to infinity, for the quantity 1 over 5k plus 3. Now, this is our given series. We might think of this as representing in the argument here. This is the summation from k to infinity for what would be a sub k, right? That's going to be our given series here. What we're going to want to do with this given series is compare it to a known series. Right? When I mention a known series, we're going to want to compare it to a series where we know the convergence or divergence of that series. Now, where students, right, struggle here is trying to come up with that comparison series. And what I go back to, folks, is I go back to the idea that there are a few cases for series where you happen to already know the behavior. And we have brought these up in past sections of notes. One of those series, particularly in this case here, is the case for what we call a geometric series, right? If I was to ignore, right, in this given series, this quantity plus 3 in the denominator, if I was, for instance, just for the moment, to delete that quantity plus 3, right, this given series would be a geometric series. It would be a geometric series where our value of r would be equal to 1/5, and the absolute value of that being less than 1 would indicate that it's convergent. But we don't have that case. What we have is the case for 1 over 5 to the kth power plus 3, right? We have a variation of that geometric or that convergent geometric series. But what we can do is use the comparison test up here, right? What we're going to compare to is that convergent geometric series, right? This series can actually be compared to that series given by the summation from k equals 1 to infinity for 1 over 5 to the kth power. That is this case here for a convergent geometric series, since the absolute value of r, which does equal 1/5, would be less than the value of 1. Now, if we plan to use the comparison test in a comparison to this infinite series, what we're going to have to show here is that the terms of a sub k, 1 over 5 to the kth plus 3, are always less than or equal to the terms of the comparison series here, the known series values, 1 over 5 to the kth power. All right? In order to use the comparison tests, if I bring this note into view, right? In order to use the result, right? In order to use this result to show that this series is also convergent by comparison test, what we're going to have to show, right, is that the arguments of our series a sub k are always less than or equal to the arguments of 1 over 5 to the kth power. All right? What we can note here, if we look at that inequality, right, is we can note in that inequality 1 over 5k to the kth power plus 3 being less than or equal to 1 over 5k does imply 5 to the kth is less than or equal to 5 to the kth plus 3, right? Or that 0 must always be less than or equal to 3, right? right? One way that we can go about showing that this behavior is always true for all values of k as k heads off to infinity is to set up the inequality statement that we are trying to show is true and manipulate it using algebra into what is always going to be an obviously true statement. What we notice here is it is obvious, well, not obvious here necessarily, that this quantity on the left will always be less than or equal to this quantity on the right. But there is an algebraic process that says I can cross multiply, right, across this inequality to produce this statement here, 5 to the kth less than or equal to 5 to the kth plus 3, right, using algebra, right? We can actually cross multiply here, I should say, without changing the direction of the sign. What we note is we could multiply both sides by these two denominators. And because k here is going to be heading to infinity, these quantities will, well, any power, right, of a number will always be positive. So what we do note here is that this will always be positive and this will always be positive. So multiplying both sides by a positive isn't going to change the direction of our sign. And we're able to draw this conclusion when we cross multiply. Right? Now from that conclusion, it still may not be obvious that the left-hand side now is always less than or equal to the right, even though we can kind of start to take note that the left-hand side is really just 3 less than the right. Right? But if we subtract 5k from both sides, which does not change the direction of the sign, we can actually turn this into what is obviously a true statement, that being 0 is always less than or equal to 3. So with a little bit of algebraic manipulation here, we can show that this is true for all values of k as k heads to infinity. Right? Note, this implies this or this as a result, right? Which we can point out is a true statement for all values of k as k heads to infinity. Thus, by the comparison test, since the arguments of our given series are always less than or equal to the arguments of the known convergent series, we can conclude that this known convergent series, right, convergent geometric series, well, I should say, and that convergent geometric, or that geometric series we're comparing to is also convergent, right? We can show that the given series is convergent. Now, it sounds like my neighbor's lawn service is showing up here to cut her grass. So I'm going to pause for right now, and I'll come back in a moment or two once they finish cutting to finish up this video. All right, folks, it looks like they may be done next door. So let me continue here with another quick example. We might consider the behavior of this infinite series, right? In this particular infinite series, we are going to want to compare to some other series where we know the behavior of that series. Now, what we might consider comparing to, again, is we can point out that this series does resemble a series that we are familiar with. And we are familiar with its behavior. Even though it's not explicit here, if we were to, for instance, remove this minus 5 in the denominator and reduce, right, the fractional value, that would produce the series given by the divergent harmonic series, folks. And that is going to be the series that we're going to compare to. Right? If you take note, the series I originally put up here looks a lot like the divergent harmonic series, the case for a divergent P series where P equals 1. All right? It's not explicitly, right, in a form that resembles it, but with a little manipulation, as I had noted, it certainly can be made into what would look like a harmonic series, right? So what we are going to compare to here is the case for the divergent harmonic series. Now, to use the comparison test, we are going to have to show that the arguments of this given series are always bigger than or equal to the arguments of this given series. Right? For all values of k as k heads off to infinity. All right? So we had noted, as in the previous case, we are going to have to show, or similar to the previous case, that this series here's terms are always bigger than this series here's, when it is the case that we're comparing to a divergent series and trying to show divergence in terms of behavior. All right? Note, in this particular case, if we compare the two, it may not be obvious initially that this series here is always bigger than or equal to this series here on the right. Right? But if through algebra I can manipulate this inequality into what would be obviously a true statement, right? I can conclude that this is the case in this situation here, right? And what we would note, if we do a little cross multiplying, which again for values of k greater, k that is heading off to infinity, you are going to be dealing with positive values, so multiplying both sides or cross multiplying here is not going to affect the direction of the sign. And k times k squared is k cubed minus 5 times 1 is k cubed minus 5. And in that format, it may be a little bit more obvious that what we're dealing with here is certainly a true statement. But if you're still not seeing it, you can always subtract k cubed from both sides and actually have the statement 0 being greater than or equal to negative 5 as seen here, which obviously without much argument can be shown to be a true statement. So, since this is always true, and the series we're comparing to for 1 over k is divergent, this being true, the terms of our given series being greater than or equal to the terms of the harmonic, and the harmonic series being divergent, we're able to conclude that the given series must also diverge. All right? And that's what we see here in our final statement, right? This statement that we make here in the inequality is true for all values of k as k heads to infinity. Thus, by the comparison test, since the terms of our given series are greater than or equal to the terms of our harmonic, and the corresponding harmonic series is divergent, then our corresponding given series must also diverge. All right, folks? This is the comparison test, right? It can be used to show whether a given series converges or diverges by comparing it to a known, right, series that is either convergent or known to be divergent, and looking at how the terms of the given series compare to the terms of the known series. If the known series is convergent and the terms of the given series are smaller than the terms of the convergent series, then the given series converges also. Whereas if the given series terms are bigger than the known series terms and the known series is divergent, then we can conclude that the given series is also divergent. Right? This is known as the comparison test, folks, and it can be used, as I said, as really a third test in determining whether or not a series converges or diverges. I have one more case to kind of come back and show you as we look at these first 4 tests for convergence or divergence presented in 10.4 and 10.5. I'll be back to give you that lecture shortly. Hey there, Calc 2 folks. I'm back with my last portion here in this lecture over the first 4 tests we have for determining the behavior of an infinite series, that behavior being either convergent or divergent. We've looked at 3 tests up to this point. Hopefully you have looked at the divergence test and the integral test, which were presented in section 10.4. And in 10.5, we're looking here at the comparison test, and then what is also known now as the, what we're going to see in this case is the limit comparison test. All right. All the tests have been presented in theorem form, right? So here we see the theorem for the comparison test, right, presented. Again, the comparison test is going to work a little like, or the limit comparison test is going to work a little like the comparison test, the previous test that we just had noted. It's going to look at comparing what we call a given series, the series A sub k, to some known series. And when I use the term known series, I mean a series where we happen to know the behavior of that series, whether it be convergent or divergent. All right? And the way we're going to compare these two series is by looking at the ratio we can see here of the terms of the series that were given, A sub k, over the terms of the series that we have known information about, B sub k. And we're going to evaluate in that comparison the limit as k heads to infinity. When we evaluate this limit, given by the ratio of these two terms, it's going to result in some value we refer to as L. And depending upon the value of L and the known behavior of series B sub k, there is going to be one of three results that we can expect to occur. All right? If we roll through those three results, the first result considers the case where when you calculate L, L is a value between 0 and positive infinity, not equaling 0 and certainly not equaling infinity. We can never equal infinity. All right? What is then true is that both our given series, A sub k, and our known series for B sub k are either going to be both convergent or both divergent in behavior. So if we know that series B sub k diverges, well then series A sub k would diverge. And if we know series B sub k is convergent, then we know series A sub k converges. Right? That is the first result we could have in the limit comparison test. The second result is for the case when you happen to calculate this limit and it equals 0. If it equals 0 and the known series for B sub k converges, then what we're able to conclude is that the given series for A sub k is also convergent. All right? In this particular case, it is very specific to having L equals 0 and working with a known convergent series. All right? If you can show L equals 0 and B sub k is a convergent series, then you can show the given series is also convergent. And the third result is the case where this limit for L approaches infinity. It becomes an infinite, it becomes an infinite limit, right? If the value of L actually approaches infinity and it becomes an infinite limit, and we know that series B sub k diverges, right? If we have information about our known series being divergent, then what we're able to conclude is that the given series, right, the series whose behavior we're trying to determine, would also diverge. All right? These three results are the three results for the limit comparison test, where you are going to look at calculating this value of L for your given series and some series you're comparing it to, some known series. All right? And the way it plays out is in terms of figuring out your known series, because that is really sometimes the struggle that students have here. It's a lot like the comparison test. All right? If we look at an example, we might consider the case for the behavior of this infinite series. All right? K squared plus k minus 1 over the quantity k to the fourth plus 4k squared minus 3. All right? What we're going to consider comparing this series to is a known series. Now, where am I going to derive this known series from is by simplifying this behavior, simplifying the behavior that I see happening here in the given series. And the way I'm going to simplify it is by taking note that in, again, the numerator here, what is causing a majority of the behavior to to grow like it is, right? That's going to be the quantity k squared. So in terms of determining my known series, I'm just going to ignore those second two terms. Similarly, in the denominator here, what's causing a majority of this behavior that's heading off to infinity, we would say? Well, that is going to be caused by the k to the fourth term. Where if we take note, if we simplify k squared over k to the fourth, this does simplify to the quantity of k over k squared. Oh, back up. This simplifies to the quantity 1 over k squared, right? Or what do we know about 1 over k squared? 1 over k squared is a convergent P series. It's a P series where our value of the power is P is equal to 2, and since 2 is bigger than 1, we have the case here for convergence. All right. Again, where I determined that known series was but just considering really the behavior for the first, for the numerator, what causes the overall behavior in the numerator, and that's going to be k squared, and what is a major influencer in the behavior of the denominator, and that's going to be k to the fourth. Putting those in ratio together, we can see that our comparison series would be 1 over k squared. So if I bring that into view, that is what we take note on here to begin with. And that is that this series can be compared to the series 1 over k squared, which we know is the convergent P series, since P is greater than 1. Now in the limit comparison test, what we're going to do with the given series a sub k and our known series b sub k is compare them as this ratio and evaluate the limit of that ratio, where that limit is going to be declared as the value of L. And what we're going to hope to see is either L being a number between 0 and infinity, which would allow me to conclude since b sub k is convergent, a sub k converges, or to hopefully see a value for L equal to 0, right, where since b sub k also converges, we would be able to conclude that a sub k also converges. If it so happens that we calculate this value of L and it's an infinite limit, it heads to infinity, then we are really going to have an inconclusive result. Since b sub k does not diverge, it converges, we're not really going to be able to say much about a sub k if that occurs. So let's take a look at what the value of L is. If we come down here and we take note on the value of L, it is going to be the limit as k heads to infinity for the quantity a sub k over b sub k. And up here in our given infinite series, this is our value of a sub k, and down here in our known series, we're going to find our value of b sub k. And if we put those in ratio with one another, we would form this ratio given here, which we note is a complex fractional form. You have a fraction in the numerator over a fraction in a denominator, right? That's a complex form, where to begin evaluating the limit of this complex form, complex rational form, we're going to consider the division as really a product of the reciprocal here for the denominator, right? If you keep in mind, one of the ways that we simplify a complex rational form is we consider rewriting it as a product with the denominator's reciprocal, right? If we flip the fraction upside down in the denominator, we're actually going to form this statement in our limit, which is no longer complex. And if I multiply these two fractions together, that k squared will distribute through the numerator, right? And it would form this as our argument. Where now the limit as k heads to infinity on this argument, from L'Hopital's rule or from some fundamental rules of integration for limits at infinity, we would be able to show that this simply equals the value of 1. All right? So what does that tell us? Well, since L equals 1, which is a value between 0 and infinity, and series B sub k converges, right? It's this case for a convergent P series, we're able to conclude that this given series, A sub k, also converges. Right? If we bring that result into note, that is how we would conclude. All right? Since L equals 1, right, which we could note as a value between 0 and infinity, right, and series B sub k is convergent, by the limit comparison test, we can go on to conclude that our given series must also converge. All right? That is the limit comparison test in action, folks. Let's consider one more example here. If I bring another example into view, right, we might consider the behavior of 2 to the kth power over e to the kth power minus 1, the behavior of this infinite series where our terms are given by 2 to the kth over e to the kth minus 1. Now, as with the other cases for comparison test, we are going to have to consider the series we're going to compare to. We have to determine what's going to be our known series. And as I've highlighted in the other examples, this is a rather common technique. One of the things we're going to consider doing here is removing the aspects of the numerator and the denominator that don't cause a major influence in those values. And what we would see here is removing this -1 from the denominator doesn't have much influence over the value of the denominator, and we form this ratio 2 to the k over e to the k. Where if you spend a moment with 2 to the k over e to the k, you might note that's similar to the following known series. What series we might say this is similar to? We might say this is similar to the series 2 over e, all raised to the kth power. Using a little bit of power rules, we'd be able to factor the k out of, well, not really factor, but bring the k out as an exponent on the entire ratio 2 over e, using our powers, our laws of powers, or our power rules. And we'd be able to form this series here, which we should note is actually a case for a convergent geometric series. Our common ratio here would be 2 over e. E is 2.72. So 2 divided by 2.72 will certainly be smaller than 1. And this would be the case for a convergent geometric series. All right? Notice all I did to form this was I simplified the overall behaviors, right? Not quite. One more. Oh, I'll have to add it back in that way. Right? Again, I eliminated the -1 in the denominator and then brought the k out as just a power on the fraction 2 over e, right, in value. And what that says is we're going to compare to that convergent geometric series 2 over e raised to the kth power. Right? This series can be compared to this series here, which again we note is a convergent geometric series because 2 over e is 2 over 2.72 thereabouts, which is certainly smaller than the value of 1. All right? What we're going to do now is calculate the value of L. If we consider then the value of L in this test, the actual value of L, right, the limit as k heads to infinity, for the ratio of our given series over our known series, it's going to form again this complex rational form, this complex fraction, where we understand to remove the complex nature in this fraction through algebra. We simply rewrite it by considering it a product, the numerator, with a product of the reciprocal of the denominator. And if I bring that result into view, right, that is going to imply this result here, right, where we're just multiplying the numerator now by this reciprocal of the denominator. Where when we multiply by this reciprocal of the denominator, we should note that these terms, or I should say factors, 2 to the kth in the numerator and denominator are actually going to cancel with one another. So the 2 to the kth in the numerator will cancel with the 2 to the kth in the denominator, resulting in a 1 in each of those locations. And then that statement would simplify into e to the k over e to the k minus 1. All right. So that's where we end up with this limit. Or how do we evaluate this limit? Well, we're going to rely on a little L'Hopital's. If we apply L'Hopital's rule, because notice that is infinity over infinity, taking the derivative of the numerator and denominator with respect to k is just going to yield e to the k over e to the k by L'Hopital's. So what is e to the k over e to the k? That's simply the constant value of 1. So the limit here is also going to just equal the value of 1. All right? And again, from the limit comparison test, right, our value of L equal to 1 is between 0 and infinity, and the known series B sub k is convergent. So that must tell us that our given series is also the case for convergence. Right? And that is the result we see here. All right? I scrolled down a little too far. Let me bring this up into view. All right, our given conclusion here. All right? Since L is equal to 1 and our known series is convergent, by the limit comparison test, we can conclude that the given series, right, the series whose behavior we were questioning, must also be convergent. All right, folks, that's the 4th test, and what is going to be our first 4 tests for convergence versus divergence and infinite series. These are what we might say are the four fundamental tests that we have. The 4 fundamental tests that we have for what are known as our non-alternating series. These are series whose terms are always positive. We are going to have a couple of other tests that we're going to present. There is going to be the test that comes up in section 10.6, which is known as the alternating series test. That's a test for alternating series. And one of the things we're going to encounter in that test is what we call conditional convergence versus absolute convergence. What that brings then about is a way of actually testing for absolute convergence, which involves a few more hybrid tests, we might think. That being what we call the ratio and the root test. So I call these the first 4 fundamental tests that you're going to want to take note of, but there are 3 more tests that we're going to have to consider. Those are going to be the tests for what we call the alternating series test, and then what follows that, which is going to help us determine absolute versus conditional convergence, which is going to be the root and the ratio test, folks. So I'm going to present those in the next videos. I also have a video I want to put out that deals a little bit with approximating values of series. There's a couple of techniques we're going to look at with respect to approximating series, folks. And that's going to wrap up Chapter 10 for us when we complete those ideas. And soon enough, we will be over into Chapter 11. So hopefully you're keeping up with these videos, and I will see you next time. Bye.